All right. Hi, everyone. Welcome to week 5 slides for statistical models. Today, we're going to continue our talk about multiple linear regression and learn some new concepts with that. So to recap, what we've talked about so far for multiple linear regression is the model statement itself, how to assess assumptions or see the validity of inference for our multiple linear regression model, how to construct new predictors from current explanatory variables, making or constructing interaction terms in our model, and then also how to include categorical predictors in our model and how exactly that works. So those are some concepts we've already talked about, but there's a lot to discuss for multiple linear regression. And today we're going to continue our talk about these concepts by looking at the correlated predictors issue, which is also called multicollinearity, how to test subsets of predictors. So we've seen how you can use like a hypothesis test to test an individual predictor if it's important or not based on its p-value. But it might be the case that we have like 5 predictors and we want to just test if a set of 2 are important together or not at the same time. So that gets a little bit more complicated, so we're going to talk about how you can do that. Added variable plots, which are ways to visualize the relative importance of a variable, an explanatory variable, after accounting for the others. And then also just methods in general for how to select predictors or explanatory variables for our model, since it's not always ideal to just include every possible predictor that we have. And we'll talk about why that is some. So to start with the discussion on correlated predictors, we can recall that one measure of association between 2 quantitative variables is the correlation coefficient. And this is denoted by R, and it describes the strength and the direction, be it positive or negative, of a relationship between 2 different variables. So we've seen this so far in looking at the correlation between our response Y and our explanatory variable X. But we can also look at the correlation coefficient between the explanatory variables themselves. So recalling back to the National Health and Nutrition Examination Survey data, Nhanes data, where we modeled blood pressure of people using their age, BMI, cholesterol, and their heart rates. So this was a multiple linear regression model. And we're going to look at the correlation between, just to start, the response, blood pressure, and a predictor, say, age. So I'm creating a scatter plot between age, that's my explanatory variable X, and systolic blood pressure, the Y response variable. And then I'm also adding to the main title for the plot, the correlation, which I'm rounding to 2 decimal places between the 2 variables. So here we can see, and again, this \n just returns the next part of the string for the title to the next line. That's what this \n is doing. So here we can see the scatter plot, and it looks like, based on the plot, that there is a positive relationship between age in years and systolic blood pressure measured in millimeters of mercury, because as we go from left to right, the points are increasing in value. And from the main title for the plot, we can see that the correlation, which I had R calculate and print here, is 0.51. So the correlation is bounded between -1 and 1, where 1 is indicating a perfect positive linear relationship, 0 is no linear relationship, and -1 is a perfect negative linear relationship. So 0.51 is moderately strong. That's quite a strong correlation, actually, to see for real-world data for 2 variables that are not deterministic of one another. So age is very much related linearly to systolic blood pressure. So this is a good thing, that there appears to be a good, strong linear relationship. That's a great thing to have going on if we want to fit a linear regression model. Another variable we can look at for modeling systolic blood pressure was the heart rate in beats per minute. So here it's a little bit more difficult to see, but if we imagine the line of best fit going through here, it would probably look something sort of like this. It would be a negative relationship in the data. Maybe not even that pronounced. It might be more like this, but still a negative downward slope here in the points for this line of best fit. And this is indicated by the correlation coefficient between them being minus 0.1. This downward slope here. So certainly it's not as strong of a correlation as with age, but there's still a correlation between blood pressure and heart rate here. But we can also think about how there is potentially a relationship between heart rate and age. This is something we would expect potentially, but we can use a plot here to investigate this. So again, these are our two explanatory variables we're looking at the relationship between now. And we can see here, again, it's not as clear as the very first plot, the relationship here. But with the line of best fit, it's probably going to be something like this. So it's, again, a negative relationship in this data going on here. And we can see confirmed by the correlation coefficient calculated by R, minus 0.23. Yes, there's a negative relationship between age and a person's heart rate, their resting heart rate on average. So intuitively what this means is as somebody's getting older, their heart rate, let's see, as someone's getting older, their heart rate is tending to decrease. Or inversely, as their heart rate is higher, they tend to be younger on average. That's what this plot is telling us. So the main takeaway is that heart rate and age are correlated, and they have a negative correlation. But they're just the explanatory variables, so it might not be clear why we care about this. Well, some funny things can happen with our regression model when the explanatory variables themselves are correlated. Ideally, they would be perfectly independent of each other. Their correlations would be zero. But that's not really the case ever in practice, so that can cause some issues. And here we'll see, so if we fit a model, just a simple linear regression model using age for systolic blood pressure and printing that output, we get what we'd expect again, that there was a positive relationship between age and blood pressure. And the p-value of 0 is indicating that it's statistically significant, the p-value being very small. Okay, so nothing surprising there. If we fit another regression model where we're modeling blood pressure again, using heart rate, which they had a negative correlation if we recall back to that second scatter plot we looked at, and obtaining the regression output here, we can see that indeed they have a negative, there's a corresponding negative regression coefficient for heart rate used to model blood pressure. And again, this is not surprising. We saw a negative relationship on the scatter plot, so the slope between heart rate and systolic blood pressure is also negative. And again, the p-value being less than 0.05 or being very close to 0 is indicating that this linear relationship is statistically significant. So here's where the problem comes in. If we fit a two-predictor multiple linear regression model modeling systolic blood pressure, where we have age and heart rate as our predictors, we can imagine we would expect age to have an estimated regression coefficient that was positive and heart rate to still have an estimated regression coefficient to be negative, which would be the case if age and heart rate were independent, if their correlation together were 0. But what we actually see when we print this model output is that age still has a positive relationship with systolic blood pressure after accounting for heart rate, but heart rate now has a positive relationship after accounting for age. So it's flipped. It's no longer negative, this relationship with heart rate. And yet it's still statistically significant as well. The p-value is less than 0.05. So how can this be? We have this relationship that we described from the same data set in terms of how heart rate and systolic blood pressure relate to one another. And this relationship and how we interpret it has changed drastically without changing our data set even. So this happened because of the correlation between age and heart rate, or what is called multicollinearity. So when they're correlated, weird or strange things can happen with the signs of the estimates and also the magnitude or relative importance of the estimates. Here they're both statistically significant still, but it certainly could have been the case that heart rate became not statistically significant after accounting for age. And so that's sort of the key thing here, is that the reason the relationship changes based on the output here is because this is representing, this table is describing, for example, the effect of heart rate after accounting for age of the person. It's not just the relationship between heart rate and blood pressure alone, it's after accounting for age. And similarly for age, this is the effect of age on blood pressure after accounting for heart rate. It just turns out that the effect of age after accounting for heart rate, 0.443, if we go back to its simple linear regression output, 0.439, it's very similar still. So age just happens to not change that much, but the effective heart rate goes from minus 0.14 for its regression coefficient to 0.028. So it changes sign, which is problematic for interpretations. So again, when this is present in the data, when this correlation between explanatory variables is present, we call this multicollinearity. And it causes, mostly the main problems are in the interpretation of individual regression coefficients. So interpreting the relationship between different variables now gets a bit murky and is no longer valid. So for example, when this is a serious problem is when explanatory variables are, say, exact linear functions of one another. So if we had x1 is equal to 3 times x2 plus 7, so this is a linear function of x2, then actually a unique solution doesn't even exist for the least squares estimates, essentially for the regression estimates that R obtains. There's not one unique set of regression estimates that solve this anymore, if this is the case, if the explanatory variables are a linear function of one another. So again, this causes problems in terms of interpreting the effect of an explanatory variable on the response. So what can we do? Well, we can check for correlation between all the explanatory variables for one thing. So here, for example, I'm using the core function, which stands for correlation, and then inside this code, I'm specifying the Nhanes dataset, and then a square bracket, and this first argument is indicating which rows of the data set I want, which observations. So I'm wanting all of them, so I leave it blank. And then comma. And then the second argument here is specifying which columns of the data set I want to look at, encased in this C function, which stands for combine. So I'm asking for the age, BMI, total cholesterol, and heart rate columns from the Nhanes dataset. And so the first argument to the core function is just a whole dataset, where here I subsetted to these 4 columns. And then this next argument, I'm just saying to use only complete observations, essentially ignore missing values. Otherwise, R gives the correlation as being missing if there's any missing values in the whole data set. So calculating the pairwise correlations, I end up with this table, this 4x4 table, since I have 4 variables, giving the correlations between all the variables. So in general, the correlation of any variable with itself is always going to be +1. And that's because they're perfectly related. A variable is perfectly related with itself. And here we can see the correlations between all the different pairs. So certainly a lot of variables are related. And this is common to encounter in real life. Age and BMI are positively related. So the older someone is, the higher their BMI is on average. And same with cholesterol, which is not too surprising. The older someone is, again, the higher their cholesterol is on average. And similarly for heart rate and age. So there's certainly all this multicollinearity going on in this set of explanatory variables. So that causes issues, again, for interpreting regression coefficients, and that we can no longer do it effectively. So instead of one way to check for multicollinearity, that's sort of a subjective way, is to just look at the correlations between pairs of explanatory variables in this way. Another thing that we can do to assess multicollinearity is to calculate what's called the variance inflation factor for each predictor variable, or VIF is what it's commonly referred to as. So for explanatory variable xi in a regression model, the VIF, the variance inflation factor, is given by this formula here, 1/1 minus its r squared, where r squared is this coefficient of multiple determination where you modeled that explanatory variable as a response using all the other candidate predictors. So the idea here is that if the other variables explain a lot of the variability in xi, if the other predictors explain a lot of the variability in xi, then r squared will be high, as in it will be close to 1. And so this denominator will be close to 0. As r squared is closer to 1, this denominator gets closer to 0. And then this whole term, the VIF, will get very big because 0 in the denominator makes this whole quantity very large. So to reiterate that again, the more the other explanatory variables explain in xi, the higher its variance inflation factor will be. Which is indicating a higher amount of multicollinearity. And a general rule of thumb, so there's not like a set rule that everybody uses. It's not like if a VIF is greater than 10, then there's multicollinearity. Otherwise, there's not. Unfortunately, like a lot of things in statistics, there's sort of these rough rule of thumbs. So for VIFs, people tend to say if it's bigger than 5, which is corresponding to an R squared of 80%, then there's multicollinearity so severe in the data that maybe you should remove one of the predictors in order to reduce the VIFs. We can still use models in general for predictions, even if the predictors are extremely correlated. But the thing is, it invalidates interpretations of the regression coefficients, as well as the p-values, confidence intervals, and hypothesis testing. So a lot of the stuff that encompasses what we'd call statistical inference. We can no longer do hypothesis tests, interpret p-values, or coefficient estimates. What can we do though still? We can still fit our model and obtain predictions. So if your only goal is to have predictions, to get new, better predictions for the future, then multicollinearity is not as much of a problem. But if you want to be able to explain relationships in the data, for example, it might be important to know that as age gets larger, a person's cholesterol tends to get larger on average as well. That might be an important thing for doctors to understand. So in that case, it's important to not have multicollinearity going on. But if we just want to predict someone's blood pressure based on a lot of factors, then we want to include more variables in our model, even if they're correlated. So it's sort of a difference of what you're aiming to do, better prediction or understand relationships in the data intuitively. So to calculate the variance inflation factor in R, there's no function that's in base R, so the prepackaged sets of functions that come with R already. But there is this nice companion to applied regression R package, the CAR package. So we can install it using this code, which we only have to run once, install.packages. And then we can load the R package using the library command here. And within this function, after we load it, we'll have this VIF function that we can use around our model fit object to get the variance inflation factors for each of our explanatory variables. So here we have 4, so we should be able to get the 4 VIFs, one for each predictor. And so here what we can see actually is that none of the VIFs are even close to 5. So if we remember back, 5 was our rule of thumb for when to be concerned. All these variance inflation factors are quite close to 1 actually. But we did see, based on the table of correlations, that there certainly is multicollinearity going on here. But based on the variance inflation factors, that seems to suggest it's not as much of a problem. So this is where it sort of gets to be that there's not always one right answer with regression modeling. Personally, how I would handle this, again, is it depends on what you're trying to do. So if I'm just wanting good predictions, then yeah, this is fine to keep all the explanatory variables in the model. But given that I see the correlations are so high between the variables, I probably wouldn't consider the interpretations of regression estimates from this full model fit to be valid. So I wouldn't interpret those slope estimates that we get from this model. That's how I would handle it. And we talked about previously, so now I'm sort of moving on from multicollinearity. We can talk about this concept of testing subsets or sets of multiple predictors simultaneously. So before we've seen how we can use a t-test to test a single predictor, whether it's statistically significant or not, one at a time. We used a t-test statistic to do that, which is given in the output. We can also test, say, 2, 3, or just an arbitrary number of predictors at once using what's called a nested f-test or an f-test. So these are useful, especially when we have a set of correlated predictors, because they can sort of mask each other in terms of which variables are important. So when two variables are very correlated, two predictors are very correlated, one might make the other one seem less important just because they retain or give so much of the same information. So it might be beneficial in that case when predictors are correlated with each other to sort of test them simultaneously together to see if they should be kept in our model or not. And the main idea for these nested f-tests is to test if a larger model, in other words, a model with more explanatory variables, does just as well or similar to a reduced model or a smaller model, one that has less explanatory variables in it. And a model that has less predictors in it is said to be more parsimonious. That's sort of just terminology in stats. Ideally, we want the most parsimonious model possible that still does a decent job in explaining our response. So we want to use as few explanatory variables as we can, while still doing a pretty good job of explaining why. And so this is because, in general, it's easy to overfit your data accidentally by including too many predictors. So overfitting is pretty much just like when we are modeling noise accidentally in our data, just random fluctuations, but not the true linear relationship that is there. And sort of what I was just getting at, parsimony, or having a parsimonious model, is key. We want the simplest model, the one with the least number of explanatory variables, but still does a good job of explaining the response. And so for this nested F-test, we have a formal set of hypotheses again. And in particular, what we have is that testing a set of predictors using this nested F-test that we want to consider removing from our model or not. Our null hypothesis HO is that all the betas, the beta sub i's that we're considering removing, are 0 for all predictors in the subset. And then the alternative hypothesis is that at least one of the predictors is non-zero. The coefficient for the predictors is non-zero. So it doesn't have to be that all the variables are important or have a linear relationship with the response. It's just that at least one of them does. In the larger model is called, the model with more predictors that we're considering is called the full model. And so this has all k number of predictors that we're considering, while this reduced or smaller model that we're considering sort of trimming down to is called the nested model, and because it's nested within the full model. So this just excludes the predictors that we're considering removing. And to calculate this F-test statistic for this nested F-test, what we do is we calculate the sum of squares model for this full regression model with all the predictors minus the sum of squared models for the smaller model, and that in parentheses divided by the number of predictors that we're considering removing, and then divided by the SSE, the sum of squared errors for the full model divided by n minus k minus 1, where k is our full number of predictors. And so this is called an F-test because it conveniently follows an F distribution, just like the previous F-tests we've seen from before. And so R will give us this test statistic value and its corresponding p-value, which allows us to test if the set of predictors is statistically significant or not. In other words, do we have evidence that they're important in explaining the response variable, even with all the other predictors already in the model? So this is a generalization of the overall F-test that we saw just for testing our regression model as a whole, in that we're sort of extending it to this case of considering two models at once. Whereas the other F-test that we looked at before was actually a nested F-test as well, where we were considering the full model just to be our model that we were testing, and then the reduced model was actually a model with no predictors at all in it. So we've actually already seen a nested F-test before. We just didn't know we were comparing two models. But it's actually, this is just a generalization of it. So to start next time with the next video on the slides, we'll look at using a nested F-test for the Nhanes dataset and seeing how we can compare a full and reduced model with that. So thanks, and I'll see you guys then.